Good afternoon. Don't be put off by me holding a guitar. This is really an episode of my engineering Oddcast. The subject today is about innovation and research and development, and I've been wanting to do this for a while. As I've said previously, I haven't been able to take you inside an R&D process because in general I'm doing R&D on behalf of companies and I can't expose their secrets. At the moment I'm in the middle of an R&D process on guitars, so I am able to talk about it if I choose to, because the only secrets I'd be divulging are mine. Research and development or product development or innovation are things that people know they want to happen, but they think there's some kind of mysterious genius required to actually do it. And in fact, there is a repeatable set of steps you can follow to get research and development and innovation done. And I think it would be helpful to a lot of people and businesses to know what those are. So first decision you must make is to do it. And the decision you must also make is in what area are you trying to innovate? So in this case, I want to make a new design of guitar. And I am eventually, I think, going to attack all parts of the guitar. But for the purposes of somewhere to start, I've decided I'm only going to change things on the guitar body. I'm not going to try and do anything innovative in the neck, in the tuners, in the strings themselves, the frets, the fretboard, the nut. So all of these existing components I'm just going to treat as though they're fixed entities for now. So that immediately gives me somewhere to start. And the first thing that I do when I'm trying to do innovation is I think about, just in my mind, what are my options, what am I trying to achieve? And for purposes of talking about it, we'll refer to that part of it as the mental model area. Okay, so we start any kind of process of innovation with mental models, and we apply, we think of options, we filter them out based on our own experience, which hopefully you have some. It's very hard to innovate in an area where you don't know anything, but we'll talk about how to do that as well, or I'll try to remember to talk about how to do that. But the first thing I do is I have my mental model of what a guitar body is, and I think about what I might like to do. So I'll pick a ludicrous example. I've obviously, guitar bodies are traditionally made out of various kinds of wood. I could choose to try and make one out of laminated wood or chipboard, or I could choose to make one out of plastic or steel, or cardboard or cheese. Now, my knowledge and experience allows me to say that a guitar body made out of cheese is such a bad idea that I will filter it out at the mental model stage. I will not allow that idea to progress any further in the innovation process. And the same with a guitar made out of basic cardboard. But I might file that away. Like, I might identify the problems with making a guitar out of cheese. It would go moldy, it would smell, bits of it would flake off, and say, okay, so we've identified that. So all of those issues are things that we now have already decided are bad properties for a guitar material to have. So I don't need to spend I honestly didn't need to spend very much time coming up with reasons why a guitar made of cheese would be bad. But if I were to ask, should I make the guitar body out of bread, I can immediately say, well, look, we already determined that things that go moldy are a bad choice for guitar body material, so bread's immediately out for that reason. You don't need to rethink through everything in the same depth if you've already answered that part of the question. And that brings me to really what the core purpose of R&D is, like what you should be focusing on when you're doing R&D. What you're trying to do is accumulate useful knowledge. And if you're working on your own, you can attempt to rely on your memory for that. I would advise you not to do that and to have a notebook in which you note down anything you've done any R&D about in the mental models or physical models or other kinds of testing. We'll talk about those in a moment. But anytime you make a decision or make a determination about something, make a note of it. It will help you to recall it later. And if you're a business trying to get your employees to engage in R&D for your business, you really need to have in place a good process for capturing that knowledge that the outcome of the tests that they do, what they determine to be true and false during the R&D process. Because if you are storing that knowledge just inside their heads, your business doesn't have anything, and your business should be conducting R&D in such a way that the useful knowledge is captured by the business. It shouldn't be doing it so that it's captured by the employees or just lost, which are the other realistic options. So if we were thinking about doing a cardboard guitar body, we would say, well, cardboard on its own is too floppy, but it doesn't flake apart particularly, it doesn't rot. So maybe it could be part of an aggregate system that allows us to use it as a component. And it might be cool to be able to say this guitar body was made from 80% recycled cardboard if we can find something else for the remaining 20%. So we'll file in our R&D organization system, we might make a record of a cardboard guitar body. Like obviously on its own we cannot get it rigid enough, but is there a way we can find to use cardboard as a filler or as a aggregate material inside some other plastic matrix to make a material that is rigid enough to form a guitar body out of that would work? And maybe that's a future research direction that we might go in. The next stage of R&D after mental modeling, and that's where mental modeling is where you have them, generally speaking, you'll have an idea, you'll filter it through mental modeling. Like if you do not think there's any chance it can work, then you stop there. As I say, you might make notes on why you first considered it and why you're sure it won't work, but then you leave it. You don't take it any further than that. The next step after the mental modeling is generally some kind of computer simulation. So all of the parts that you see here were modeled in some 3D computer-aided design program and were assembled in the computer simulation domain into a guitar before they were ever made real and assembled into a guitar in the physical world. And some components that had passed the mental modeling sanity check did not pass the computer simulation sanity check. So I can't show you those because they were never made real. And I don't want to bother capturing my screen and showing you my secrets. But So there are some ideas which were reasonable enough to pass mental modeling, and reasonable enough that I invested the time to make a computer model of them, and that then in the computer simulation domain I could see would not work to make a guitar. So some ideas got cut off at that stage, and that's normal in all R&D domains, that you will have you'll allow stuff through your mental modeling stage that will then fail at one of the later stages. That's how it's meant to be. You just you don't want to chuck away an idea that might have worked, or that you every business and or every R&D project, you'll have your own kind of tolerance at each stage for how likely does it need to be that it works before I let it through, because you're never going to be absolutely certain. Like, there might be a really good way to make a guitar body out of cheese, but I am never going to try it because I'm sufficiently certain in my mental modeling that it won't turn out well. And the same with some of the parts I rejected at the computer simulation stage. Like, they were good enough thoughts to get through my mental modeling questions, and they are not good enough in computer simulation to make me think I need to see it in real life. I could have been wrong, and I accept the risk that I was wrong to get rid of some of those ideas. Once we get to the past computer simulation, the next stage for most R&D is going to be making some kind of model of the system. Now, all of this applies, by the way, to software systems that you would preferably think about it, do some kind of simulation of, like, to sanity check if we had made this system to the performance characteristics we can expect, would it work? And then you would go and build some kind of small scale or different scale, or at least different context implementation of what you're thinking about doing as a way to test the idea in a model format. So in this case, we're looking at my model guitar body, and as you can see, it is actually at 1-to-1 scale. So in what sense is it a model? Well, it is not constructed of a realistic material for making guitars out of. It is not constructed from a unified piece as you would with a real guitar. These bits of gaffer tape here are structural. They're not part of some kind of stylistic decoration. And it's therefore an approximation for, if I made a guitar body shaped like this, what would it be like? And I think it's worthwhile at this point to talk about whether you should, how to make an innovation platform for your R&D project. So in this case, I knew I wanted to innovate on various parts of the guitar body and how it works, and I was going to treat the neck as fixed. But I've also componentized the guitar body into many more pieces than any production guitar body would ever be composed of. So this piece to which the neck is attached is a component. You can see the borderline here. This piece, which contains only the neck pickup, is a component. This piece, which would contain the middle pickup if there was one, is a component. This piece that would contains only the bridge pickup if there is one, and does, is a component. This piece that contains the bridge and tail piece of the guitar is a component. The controls and lower ergonomic body interaction parts of the guitar is a component. This upper body interacting parts of the guitar are actually 3 components. So you can see the joins. What this has allowed me to do is mix and match various options that I have for things that are not fully independent of each other, choices wise, but partially independent of each other. So what I mean by that is the neck pickup component here isn't completely independent of the controls, because it has to be electrically connected and the controls have to make sense and be able to control this neck pickup, and similarly for the bridge pickup. But I do not have to I have made them independently variable, and that allows me to, if I wished to, I could put a single coil or Strat or Telecaster style single coil pickup here, or some other single coil pickup here, without having to change any of the wiring and controls. So I could also put humbuckers or Jazzmaster pickups in these places. In the case of humbuckers, it wouldn't be a splittable system, but I wouldn't need to change the controls if I just wanted to use them straight. The major dependency I have is if I wanted to have 3 pickups, then this 3-way control switch wouldn't work. I'd probably want to use a 5-way. And if I wanted to have splittable humbuckers or make some kind of no tone control, no switching, single pickup guitar, these controls wouldn't work. But what I've done is I've created a system where I only need, if you've been paying attention, or I don't know how many wiring options I would have for pickups, and I would only need 3 different wiring options for the controls for all of those to be able to make sense. In here, I could install a humbucker or a Jazzmaster pickup or a Telecaster pickup or a Strat pickup, same in the middle, same in the neck, and I can change the controls to suit that. And basically, I can make any configuration of pickups and controls that I have ever wanted to make in a real guitar by just mixing and matching a few components, much more cheaply than it would have cost me to manufacture all of the different bodies from a piece of wood. And similarly for the upper piece, this pretty much is independent of the rest of the body, other than it's not, it's nice if it lines up at these ends, but I can make these components vary however I want in order to get the ergonomics I'm looking for. And it's important to say, because I do not wish to lead anyone down the wrong path, what is fitted to this guitar is a fairly random combination of parts that I consider to be okay, parts that I consider to be terrible, and parts that I consider to be the best version of that component. I have other versions of everything that you see here, and I am not going to tell you which is which. So that's the way in which I'm protecting my IP at this time. I'm willing to show you my in-progress R&D project and talk about it, but I'm not going to disclose to you any of the useful knowledge, which is what's good, what's bad, what works, what doesn't work, and so on. The concept here in this model space, where it's a real, it's close to real, but it's not real, is you're trying to make sure that you learn more than you could have learned in the computer simulation space, but you're doing so at much less cost than building a real product. So that's the point of this phase of R&D. And at some point, potentially, the end game of this phase in this particular case is I have a model of what I think, all of the parts that I think are best, and that's then ready to go to a final design validation process where I would make the whole thing out of a proper guitar material with whatever the pickup configuration I'd chosen was, with whatever the controls configuration I'd chosen was, with whatever the upper body configuration I'd chosen was. And if we've gotten through that, it would have whatever the prototype, the modeled replacement neck and tuners and whatever looks like. And that would be where this model phase would end. And then we would go and make a real one to verify that a real one can be made, and to verify that the approximations we've made by making it a model didn't actually mislead us too much. And that's a good place for me to introduce the word correlation. Now, what we mean by correlation in an R&D process is the extent to which what you're thinking about in one of the, or what your result is from one of the model spaces corresponds to what the result is in reality, or sometimes in the next more expensive model space. So if we go back to mental model space, where I was thinking about, can I make a guitar out of cardboard? If I had much less experience making guitars than I do, I might not know that cardboard is not going to be sufficiently rigid to make a guitar, and I would have allowed that idea through into computer simulation space, and I would have spent some time and resources there on it, and that would have been wasted money because it wouldn't work. And that would have told me my correlation between mental model and reality, or at least mental model and the computer simulation, is too weak for me to be usefully doing stuff in that mental model space. And I need to go and try and do some improvements to how I think, which realistically means get some more experience about what's important in guitar design, so that I can improve that correlation factor. Similarly, correlation is the explanation for, suppose that someone comes out next year with a guitar fully made of cardboard and that works fine. That would say that my current correlation to mental model space is bad because I've thrown away an idea that was actually good and should have been allowed through. It's possible, I freely admit it. So you can think of it as your chance. It's your chance of error, and ideally you want to have everything as closely correlated to reality as possible. So if we look at this guitar, because it's hollow plastic, or largely hollow plastic, this guitar body weighs less than it would do if it were made out of wood or some other more reasonable guitar manufacturing material. And that means that when I'm trying to test how it feels, the weight distribution is wrong. The neck is heavier than the body, but in an unrealistic way. And so while I'm evaluating this guitar in this model space, I have to try and compensate for that known error in my evaluations, which is itself a guess at how much compensation I should allow. So another chance to introduce an error. Now, there's nothing. I've chosen to do nothing about this. If I were trying to do this on a larger scale, or where I was going to have people who do not have the capacity to try and make allowances for that deviation were going to test this, I would have to I would have designed this plastic guitar to have extra holes in it that I can glue steel or tungsten weights in it, so that the weight distribution and overall weight of the instrument is realistic for if it were made out of wood. And then I would ask people to evaluate that, not the much lower weight plastic version. That's an example of correlation between reality and physical model space. The other thing you're always looking to do is get the correlation as good as you can be between reality and the cheapest solutions that you've got. So let's talk about a concrete example, which is the pickups. I've said I can change these to whatever pickups I want and put them wherever I want. And that's true. But in order to change this neck pickup, I need to slacken the tension of the string so that it's safe, change out this component, which involves untaping and retaping a lot of the body components to put the new thing in, fix up the wiring again. Not too difficult. It's done with quick connect plugs because I planned ahead, but it still takes some time. And then I have to reassemble it, tune it back up to pitch before I can test it. And there's a chance that when tuning, I'll snap a string. That happens about one time in 10. So let's say it costs me 2 hours of work and approximately 60 pence in strings every time I want to try a new pickup. Is much cheaper, let me be clear, it's much cheaper for me to do that than to machine a new guitar and completely guitar body out of wood with the right pickup hole for the pickup I now want, and then assemble that together. That would be a couple of days of work and always need at least one, maybe two new sets of strings. So we're talking about 16 hours work minimum, and let's say £12 in strings. So I'm way ahead of if I assume my competition are idiots and have not built a guitar like this, I'm way ahead of them in my R&D costs. But I can potentially get that down even lower if I can find a way to shift the experimentation with pickups from the model domain into the computer simulation domain. This guitar has the technology that should enable me to do that. So I have pickup actually built into the bridge system here, which is what's allowing the synthesizer to make sounds when I make. So that is not the sound of a guitar. That's the sound of a synthesizer, and that's being controlled by my playing on these strings. Let me play a. Just to prove that all 6 strings work in the synthesizer. So what I've got here is independent, the ability to independently sample each string separately from the others and to run that through a synthesizer. So if I want to shift this pickup choice question into the domain of computer simulation, I actually can do that. I can have, instead of the synthesizer making nice sparkly noises, I can have it pretend that have it simulate the sound of, well, what if I had a Strat neck pickup here? Or what if I had a Les Paul neck pickup here? Or a modern EMG pickup in the neck? Or what if I had the bridge was a Fishman Fluence? Or what if the middle was a Seymour Duncan P90 in a Jazzmaster package? In theory, if I've got the synthesizer models for those sounds correct, I can use the string information to give me the attack and the volume envelope and all of that stuff, and have the synthesizer make the correct sounds, and then I can evaluate what the pickups I want to be are just by sitting down with the guitar in one configuration, playing a little bit, changing in the computer simulation domain what the pickups are, playing a bit more until I find the perfect combination for myself. Now, all of that could be done without having any pickups in this real guitar, except that you do need to be sure you've got correlation. So I have in here got a neck P90 and a bridge P90. If I tell my synthesizer to sound like a bridge P90, please, and then play it, while I'm playing also the bridge P90 sound for real on the same guitar at the same time, I can check that those two sound alike. And if they do, I know I've got correlation between my model domain and my computer simulation domain on the question of pickup choice. I would also, if I'm doing my due diligence, and of course I am, need to have a real guitar with a P90 bridge and a P90 neck and verify that this model guitar, which is obviously plastic and so forth, sounds P90 like in the same way that a real guitar with P90s does. So then I've established correlation between the real domain and my model domain, and correlation between my model domain and my simulation computer simulation domain. And then I'm happy to do the pickup choice in the computer simulation domain. Now, I have correlated this to the real domain, and that works fine. I thought about what I want to say here, and I do not want to disclose how good the correlation is between my model domain and the simulation domain. But I will say, I do want to talk about the choices you might have to make when doing correlation. So without implying one case or the other, obviously, if you have good correlation on your first attempt, you can choose to do, you happily get on with your life, do nothing about it because you're already in the place you need to be. That's happy days. Another option is you find that you don't have correlation from one to the other, or it's not as close as you would like. And then you must choose how much effort do you want to put in to improve that correlation, or are you going to accept the costs of doing the R&D on that component stuff in the more expensive domain, in this case in the model domain. So I've already saved notional 14 hours and 90% of the cost compared to doing that R&D work in the real domain by having it possible in the model domain. If I could do it in the computer simulation domain, it would reduce the time requirement and costs by another minus 90%. So nearly making it free to do all of that work. But if it looks like it's going to cost me hundreds of hours to get good correlation between the model domain and the simulation domain, I'm unlikely to recoup that money, and I should just suck up that I'm going to do that development work the expensive way, at least for now, because it was overall cheaper. And that's just a straight, financial decision that I would make. Similarly, or conversely, if I was looking at it and the correlation is bad, but the next step of trying to improve that correlation costs me, let's say, 4 hours and £2 in real costs, I would probably prefer to stick that effort into improving my correlation rather than give up, just to see, if that helps. And you're continually going to make this trade-off throughout your R&D process between, do I want to invest in improving correlation between the easy way and the harder way so that I can do future work the easy way? Or do I want to accept that I will just do things in the easiest way that correlates nicely to reality, and that is going to cost me more per time than some hypothetical world where I have good correlation to an even easier way, but is cheaper and really works now? If you don't make that choice, well, you will have to make that choice. If you always choose to improve your correlation, you will have to accept that sometimes you will fail to improve your correlation in a reasonable time frame. And if you say, we're never going to do anything unless we've got it correlated all the way back to computer simulation, so that we don't need to do anything in model space and don't need to do any testing in real space, we've got 100% correlation to simulation space, it's not going to work. We don't have the mathematical, we don't have the simulation accuracy in any domain of research and development for that to work. You always will have to do some models, and you always will have to do some real testing. You always will want to do some models instead, because you can correlate reality to models and it's cheaper than just doing everything in real space. So I think that's the main things I needed to talk about. I will remind you that I am available this winter for short-term engagements. If you want help in your organization trying to get your R&D process up and running, or understanding what records you should be keeping, or thinking about where your split lines between what you're going to accept as fixed and what you're going to try and vary should be, or how to componentize what you're trying to develop, I can try and help you with that. Obviously, I'm going to be better at it in some domains than others, and there'll be a conflict of interest if you want me to design guitars for you. I'm not saying I won't do it. I'm just saying we'll both have to think carefully about how we protect our interests when we're making that deal. Anyway, I will finally say thank you for listening. I'm going to pick a different random preset from this synthesizer and play us out. Thank you for watching. Please like, please subscribe. If you want to know more about anything, leave a comment down below or get in touch with me on LinkedIn or Facebook or whatever. And most people who are watching this do know me personally, so they can do that. And I will see you in a future video. Cheerio.